Welcome to The Explainer. I am absolutely thrilled to have the executive team here today because we're looking at our manufacturing processes strictly from the perspective of an industrial engineer. Our main goal right now? Optimizing our glass production lines with a massive focus on efficiency and precision, literally mapping the material flow all the way from the raw furnace meltdown to our final strengthened product.
Okay, let's look at today's agenda. We're going to cover the anatomy of the melt, continuous flow production, discrete batch processing, advanced ceramics and fibers, engineered strength and safety, and finally, process yield and design. Section 1, Anatomy of the Melt. So, to engineer glass effectively, we kind of have to remember its foundation, that it is technically an inorganic product of fusion, right? And supercooling is the precise mechanism that makes the whole thing work. By chilling the melt at a rate way too high to allow any crystals to form, it bypasses crystallization entirely and forms a rigid, amorphous solid. It behaves mechanically like a solid, but structurally, it's like a liquid. What's really fascinating is the randomized, non-crystalline network of pure silica. Now, silica is the primary glass former that makes up at least 50% of all our commercial mixtures. Our furnaces are just constantly melting these modifiers and formers, and getting absolute control over that melt, well, that's step one for our downstream efficiency.
Moving on to Section 2, Continuous Flow Production.
When we're balancing production speed with quality, we really have to weigh our options, and evaluating these different environments illustrates exactly why we prioritize the float method for our high-grade flat glass. By feeding molten glass directly over a molten tin bath at 1150 degrees Celsius, we get this perfectly smooth, fire-polished surface right off the line. It's a massive efficiency win, guys, because it entirely avoids all those extra grinding and polishing steps you'd normally have to do with drawing or rolling methods. Now, for our continuous tubing lines, maintaining consistency and eliminating waste is absolutely paramount. We pull this off by rotating a mandrel while continuously blowing internal air pressure right through it. This air pressure is completely critical. It literally prevents the molten glass walls from collapsing inward during extrusion, which is exactly how we manage to hit incredibly tight tolerances on continuous tubing at massive scale. Section 3, Discrete Batch Processing. Shifting to high-rate bottle production. Our key bottleneck is always cycle time, so we use a rapid blow-and-blow process. First, the gob falls right into a blank mold. Next, blow down and blow back shape the parison. After that, it transfers to the blow mold, and finally, the bottle is blown and cooled. We're using pressurized air to rapidly expand a hollow gob of glass, and to stop that glass from sticking and halting our production, we coat the inner mold walls with a parting agent, like oil or an emulsion. It's super economical and honestly impressively fast. So the real crucial point here is choosing your manufacturing method based on what the part actually requires. Blowing is economical for high-rate production, sure, but it's pretty difficult to control wall thickness. Pressing, on the other hand, confines the gob with a plunger inside a split mold, yielding really high dimensional accuracy. From an industrial engineering standpoint, if a component absolutely needs tight dimensional accuracy, we have to route it straight through the pressing station. No way around it. And what about massive, specialized parts, like large architectural shapes or giant telescope lenses? For those, we rely on centrifugal casting. We are literally spinning the molten glass against the mold walls. By leveraging that high-speed rotational force to physically push the glass as it solidifies, we're relying on kinetic energy instead of relying entirely on secondary thermal shaping. That is a huge win for our overall energy expenditure. Up next, Section 4, Advanced Ceramics and Fibers. Check out the drastic difference in thermal processing required here. Sagging simply uses gravity to gently shape hot glass over a mold without applying any pressure at all, which is perfect for things like sunglass lenses. But glass ceramics? They're heat-treated to induce devitrification, which is just the technical term for recrystallization. This creates a highly crystalline structure that gives the final part extreme strength and near-zero thermal expansion. It's a total game-changer for durability. When we're talking about continuous glass fibers for composites, we are pulling them through multiple platinum orifices at staggering speeds. We're talking up to 500 meters per second. And with diameters as small as 2 micrometers, applying a chemical surface coating known as sizing is an absolute non-negotiable requirement. These silane compounds protect the incredibly fragile fibers from catastrophic mechanical wear and chemical attack during any subsequent handling.
Moving to Section 5, Engineered Strength and Safety. Thermal tempering is just a brilliant, rapid physics problem. Here's how it works. First, hot glass surfaces are rapidly chilled. Second, those surfaces shrink and enter initial tension. Third, the bulk center cools down and contracts. And finally, the outer surfaces are forced into severe compressive stress. If this tempered glass ever breaks, all that high stored energy causes it to safely shatter into small, blunt pieces. This specific breakage pattern is a critical safety standard, drastically reducing laceration hazards when our operators are handling damaged batches out on the floor. When comparing our strengthening options, it really comes down to speed versus precision. Thermal tempering is fast, it's cheap, gives us that safe, high-energy shatter, and is totally suitable for thick parts. Chemical tempering, on the other hand, is a slow ion exchange process, usually sitting for hours in a molten potassium or sodium bath. It takes way longer, but it creates that compressive stress with virtually zero part distortion, making it absolutely ideal for complex, high-precision, thin parts.
For extreme safety applications like bulletproof glass, we laminate multiple glass plates with a super tough thermoplastic. We typically use polycarbonate for its high toughness and flexibility to prevent solid objects from fully penetrating the glass. But here's the catch for us engineers. The index of refraction between the glass and the polymer layers must match perfectly. If they don't, we introduce severe optical distortion, and you literally wouldn't be able to see straight through it.
Finally, Section 6, Process Yield and Design.
Let's talk numbers, specifically 19%. When looking at our yield calculations to minimize material loss, we actually have to design backward from the final state. If our quality control metrics account for a 6% linear shrinkage during firing, our volume formulas dictate that we must design the initial dried part with a porosity of exactly 19%. Nailing this metric prevents downstream rejections, basically minimizing raw material waste while ensuring absolute dimensional accuracy. We also have to strictly design for dimensional compatibility in the real world. Think about it. Utilizing flexible rubber seals between glass and metal frames is essential to absorb differing thermal expansion coefficients. If we skip those flexible components, everyday temperature variations will just induce massive stress cracking out in the field. It's a simple integration, but absolutely crucial.
This brings us to a completely non-negotiable rule of thumb. To withstand a certain load for 1,000 hours, the maximum stress applied is about 1/3 of the maximum stress it can withstand during the first second. To prevent sudden, catastrophic failure from what we call static fatigue, we strictly enforce this baseline. The long-term load limit on any glass component simply cannot exceed 1/3 of what it handles in second one. It's our ultimate safeguard for long-term reliability.
So I'm going to leave you with this final design challenge for our factory layout as we look to scale throughput. How will we automate our material handling to smoothly integrate high-volume continuous melting with these precision batch strengthening operations? We've traced the material flow all the way from the massive continuous melt right down to specialized tempering tanks. How can we eliminate those bottlenecks and balance our entire yield? Let's get to work on scaling this workflow.